All right, welcome back to ECE484, fall 2021. So I'll remind you that there's a term test on Friday. I answered a few questions at the end of last class. I'll just kind of circle back to those right now before I do the summary. And so the test will cover up to yesterday's lecture, up to and including yesterday's lecture. So the stuff we did today will not be, the stuff we do today won't be on the exam, or is not on the exam. However, it is on the last problem set. So as I wrote on Piazza, not everything in the last problem set is going to be on the exam. Yeah, all right. So let's continue. We are finishing up our discussion of discrete time systems in preparation for control design in discrete time. And we, last class, extended our notion of stability for individual systems, right? We had asymptotic stability and Bibo stability. And then we extended that notion to interconnected systems. In other words, feedback systems. That's the interconnection that is most useful. And so we had two notions of stability, just like we had for individual systems. And the first one was a state space notion of internal stability. And it says that if you set the disturbance to 0 and the reference to 0, in other words, there are no exogenous inputs to the loop, then it doesn't matter how you initialize the plant, it doesn't matter how the controller is initialized, but the loop with no external forcing will settle at 0 as time advances. All right? And then we developed a test for that, which was essentially you form the big closed loop state space model, describing this system, and you look at the A matrix for that system. We called it the closed loop A matrix, A sub CL, and you check if that system is asymptotically stable, which boils down to checking the eigenvalues of that matrix and checking whether or not they all have magnitude less than 1. Then we had this other notion of stability, which was the input-output stability, and it's exactly the same as what we saw in chapter 2 for continuous time systems. And it says that if the independent signals, the exogenous signals, are bounded, then all the dependent signals in the loop should be bounded. Okay? And then the test for that is exactly the same as continuous time. You form the characteristic polynomial of the closed loop system, and you check that it's stable. In this case, stable means all the eigenvalues or all the roots of that polynomial have magnitude less than 1. Okay? And finally, we argued, or I just kind of mentioned briefly, that internal stability, so the state space notion of stability, implies input-output stability. The implication does not go the other way. All right? However, in practice, the two notions are in fact equivalent. So in this course, in particular, unless I explicitly tell you otherwise, we will treat the two concepts as being equivalent. And we'll simply talk about feedback stability. And so when I say feedback stability, I mean either internal stability or IO stability. Those are both valid notions of feedback stability for us. And we'll treat them as being equivalent. Okay, so we continue from there. So one of the things you've noticed about our stability tests is that it all comes down to checking a polynomial, right? So either you're checking the polynomial of the A matrix for asymptotic stability, so the determinant, to compute the eigenvalues of an A matrix, you need to solve for the roots of a polynomial. If you want to find the eigenvalues of the closed loop A matrix, you also have to find the roots of a polynomial. Similarly, if you're checking for IO stability or Bibo stability, you're checking roots of a polynomial. So no matter which way you want to do it, at the end of the day, it boils down to, does this polynomial have all its roots with magnitude less than 1? Okay? And so what we want now is a way of checking that or determining that without actually computing the roots. In other words, we want a discrete time equivalent to what you would have seen before called the Routh-Hurwitz test. So section 6.7. Identifying polynomials with roots in the open unit disk. Okay, we want to know when is it that there's when is it that a polynomial has all its roots inside of the unit disk, and the relevance of this is because all of our stability notions boil down to this test. Okay, So we're going to consider an nth order polynomial. So consider the following polynomial. Okay, and these AIs in our application, these are real numbers, right? So in physical systems and in most filters you're implementing, you are looking at real numbers. Okay, and so instead of saying this awkward phrase over and over again, polynomials with roots inside the unit disk, let's just use a terminology to describe this property, okay? In continuous time, you would say that a polynomial is Hurwitz if it has all of its roots in with negative real part, okay? There's a similar terminology for discrete time, except it's not to say that it's Hurwitz, it's to say that it's sure. So we're going to say that a polynomial is sure if all its roots, let's write that way, if all of its roots have magnitude less than 1. All right, so when I say, this terminology is a way of saying, like, this closed loop system is input-output stable if and only if its characteristic polynomial is sure, right? I could use that phrasing. That would be a way of saying if and only if its characteristic polynomial has all of its roots inside the unit disk. Okay, so the first thing we want to do is we want to get some simple, easy-to-use conditions that are necessary for a polynomial to be sure. Again, in continuous time, we know that it's necessary that all the coefficients have the same sign, right? If they don't have that, you can immediately conclude that you have a bad root. Okay? We want something like that, something that's easy to look at, not do a lot of calculations, and immediately determine whether or not this polynomial is sure. Necessary conditions for a polynomial to be sure. Okay, so there's a few listed in the course notes, and I'm just going to kind of go through them quickly. So the first condition is the following. If I replace z, so the variable in the polynomial, with the number 1, I require that whatever number I get be greater than 0. So in other words, if I give you a polynomial, you plug in z equal to 1, and you get a negative number, or 0, so obviously 0 is not good, you can conclude that it's not stable. The system is not stable. So let's kind of do a little quick argument as to why this is the case. Just to give you some intuition as to what's going on. So if we look at that nth order polynomial, what happens to it as we move z along the real axis, the positive real axis? So the picture is the following. So we'll start at 0, and we'll start going this way, plugging in larger and larger values of z, which are real. So what happens? Well, as z gets bigger and bigger, this polynomial approaches z to the power of n, right? As for really large values of z, the highest order dominates the value of pi. So if z approaches plus infinity along the real line, the value of the polynomial gets it's closer and closer to just being Zn, because all those lower powers are dominated by the highest power. Okay? And that approaches plus infinity. Positive. So that's fine. However, if this condition fails to hold, oops, if this were not true, what that means is there must be some point between 1 and some very large value of z where the sign of pi flipped. In other words, if pi of 1 were less than 0, this means that there is some point along the real axis at which the sign of pi flips. Right? Because we know that for large values of z, it's going to become positive. And if it's negative at 1, then that sign flip is going to have to happen somewhere along there. i.e., pi of z equals 0 for some real number greater than 1. And it cannot be sure, right? It has some root which is greater than 1. Okay. So that's a nice easy test. You can do the same thing at -1, same kind of argument. I won't do the proof. You can convince yourself that it's true. And so this condition is this guy has to be greater than 0. Okay? The argument is exactly the same. Okay? So you can quickly tell if a polynomial is sure by plugging in 1 or -1 and then multiplying by plus or minus 1 appropriately, and then checking the value. You know, if this test fails, bad root. Third condition is that the last coefficient here, an, this guy, has to be less than 1. Okay? And let's kind of convince ourselves to why that's required. So the proof is the following. Okay? Take our polynomial and factor it. It's an nth order polynomial. It has n roots. So let these guys be the roots of pi of z. Right? So that means I can write pi of z in factored form or unfactored form. So pi of z equals the original form, unfactored, or I can write it as a product of its roots. Okay. So now plug in z equal to 0. Well, the unfactored form gives us an. Okay. And on the right-hand side, we get this product of the roots. Okay. So now, if our condition fails, in other words, if an is greater than or equal to 1, in other words, if in absolute value, it must be that one of these numbers has to be bigger than 1. If they were all less than 1 in magnitude, there's no way that an could be bigger than 1. Right? So the argument here is that if the absolute value of an is greater than or equal to 1, it must be that one of the roots was also greater than or equal to the 1. Otherwise, that's impossible to multiply n numbers whose magnitude is less than 1 and end up with something bigger than 1. Then at least one of the roots Ci must have magnitude greater than 1, greater than or equal to 1. Okay. So 3 easy ways to check if a polynomial is sure without doing any really very minimal calculations. Right? And let's do an example of how you could use this. So I'll write down 3 polynomials, and then we'll just see if they satisfy the necessary conditions that we just discussed. So you can think about them. I'll just write them, and then we'll circle back and do them again. The n is the order of the polynomial, right? So n is, so the question is, what is the n in the second condition? So remember, we started with an nth order polynomial. So n is the order of the polynomial. So if you have a third order polynomial, n will be 3. Right? It depends on the system. Okay, so let's look at these 3 examples here, and let's see if they satisfy our necessary conditions. Well, for the first guy, without doing any calculations, I can already tell that it has a root which is greater than or equal to 1, because when I plug in z equal to 1, sorry, when I plug in, z equal to 1, what do I get? We get 1 plus 0.3, so it's 1.3, minus 1, which is 0.3, minus 0.9 gives me negative 0.6. Right? And a necessary condition for that polynomial to be sure is that when I plugged in 1, I needed to get a positive number. Okay? What about the second guy? Well, in this case, look at the last coefficient, the coefficient with z to the power of 0. It's greater than or equal to 1. So we can already conclude that it's a bad root. Okay, so we don't have to do any work, and we can say that that is not, if that polynomial is for example, the denominator of a transfer function, then that transfer function is not Bibo stable. All right. What about this last guy? I'll say we don't know. Oh, sorry, I want to add plus 0.1. Okay, you can try the 3 tests above, and it passes all of them. Okay, and so it's inconclusive. And so we'll have to do a bit more work. Right? I want to point out from that last example there, notice that we have different signs on the coefficients. In continuous time, that would be a death knell, right? In continuous time, it's over. It's not stable. But in discrete time, it could be stable. Okay, so you can't just look at the signs. That condition isn't true in discrete time. Okay. So that's a necessary condition, and so we would like conditions which are definitive, right? Necessary and sufficient, kind of like Routh-Hurwitz in continuous time. All right, and so there are conditions in the notes, but I will not teach them in class. So let me make a comment, and then we'll talk. So to obtain necessary and sufficient conditions for pi to be sure, we need to do more work. And in particular, we can use, there's two options that are in the notes. One, a modified Routh-Hurwitz criteria. Okay, if you remember Routh-Hurwitz, is you give a polynomial, you make this table, and then you interpret the table in such a way that, you know, if certain conditions hold on that table, then you have a stable polynomial. So you can do something like Routh-Hurwitz, but for discrete time. You just have to do a bit of a trick. So there's a little trick that involved using the bilinear transformation. So that's one option. The other option is another test, similar in spirit, right? You're generating a table using the data from the polynomial, and then you're interpreting the data in that table. Okay, so the second one is called, let me point out that this is section 6.72, and the jury test. So, or the jury test. So this is not named after like a court jury. Some people sometimes think it's named after a person whose last name was Jury. The jury test, and that is section 7.6.73. Okay. Please read these sections. Okay. I won't cover them in class. It's rote, right? It's mechanical in the sense that it's just a process. You just follow a process, and then you check the results. So it's not very interesting to teach, but it's useful to know. Okay, so I leave that to you, okay? We are going to move on to the last section of this chapter, and that is section 6.8, frequency response. So remind you what happens in continuous time. So recall from chapter 2. The notion of a frequency response. Of a continuous time system. Okay, and we have this picture that you've probably seen many times, but no matter how many times I draw it, I find that sometimes people don't get the idea of the frequency response. And so it's worth drawing again. The idea here is that you have G of S, Bibo stable. Right? And remember that we apply input cos omega t. So a sinusoid of frequency omega. So this is an omega, sorry. Omega. Cos omega t. And what is the output? The output, again, we've seen this already, in steady state is going to be the same frequency in, or same frequency in comes out, but with a possible change in magnitude, which depends on the Planck model or the G model. And a possible change in phase. I was speaking to someone on Monday, and they said, oh, but look, the frequency has changed, right? They said, look, this results in a change in the frequency at the output. No, that's not true, right? That is not a change in the frequency. This is still has this function has the same period as the input function. Frequency is omega, the term multiplying the time variable. This is just a constant offset. Okay. Okay, and this isn't true in steady state, right? There's some transient, but this is like the steady state output. Right? In general, there'll be some transient component, but after you wait a little bit, that's what the output will converge to in steady state. And so the question we want to ask or answer in this chapter, in this section, is one that you've probably seen before, but does something similar hold for a discrete time system? Does this hold for Bibo-stable discrete time systems? Right. So what's the analogous picture? The analogous picture is going to be G of Z, Bibo-stable. But now we're going to apply a discrete time sinusoid, cos theta k. Okay? So I remind you, in continuous time, t has the unit seconds. And so omega would have units radians per second. And that makes sense. You get cos of a radian. In discrete time, k, the discrete time variable, does not have physical units. It is an index. Right? So k is unitless. It's just the index of time. And so theta itself has to be a radian. So theta is a number between negative pi and pi. Okay, and so the question then is, what's the steady state output? Okay, and if you're into pattern matching, it's going to be a similar pattern, right? Notice that the magnitude change in continuous time depended on the plant model. And the phase changed also depended on the plant model, in particular the magnitude and the phase of a particular complex number. And so can we do something like that in discrete time? Okay, so let's derive the frequency response. So assume G is rational. Proper. And Bibo-stable. Okay, we want to see if we get a similar sort of thing. We're going to let little g of k be its impulse response. Okay, so I guess I'll mention here that the derivation we do in class is different than the derivation in the notes. In the notes, I do it in the z domain. In class, I'm going to do it in the time domain, so you see two derivations and you can decide which one you like better. But both are completely valid. I like to do it in the time domain in class because it'll connect to some things you've seen before. Okay, so we want to find the steady state output for this type of input. And so what we'll do is we will, in the time domain, the steady state response is related to, of course, convolution. We saw this last week. So to find the steady state response, we'll use convolution. Okay, so let me write down the convolution sum. And then I'm going to make a comment about it. So, I'm going to take my input for now to be the complex sinusoid. Oh. I think I've just had a technical difficulty with my setup, so give me 1 second, I need to fix something. Okay, I think we're back. Sorry about that. That does occasionally happen. But I think we're okay now. Okay, so I want to find the steady state response using convolution. Ultimately I'm interested, of course, in cos of theta k, but for now let's use e to the j theta because it's easier to do the derivation, and then you'll see how we can use it at the end. So my input here is going to be e to the j theta k, right? So this is convolution, and we argued that multiplication in the z domain corresponds to convolution in the time domain. I want to make a comment about the limits of that convolution sum. Notice that the convolution goes from k equals negative infinity to k equals plus infinity, i.e. the input was applied starting infinitely in the past. Okay. If you were to do the normal convolution, you would start at 0. And the problem with that is that you would pick up some transients along the way, right? So there'd be some transient components that show up in that convolution, and then we'd have to figure out which part is the steady state, which part is the transient. Okay? So by assuming that we've applied this input infinitely in the past, all the transients will have gone away. So if we apply the input, starting at k equals 0, there will be a transient component. In y. Okay. We're taking the limits as we do. Like this, gives us the steady state response. Which is what we're interested in. Okay, so let's continue from there. So we have y of k equals, okay, let's rewrite it. I'm going to switch the order of u and g. So I'm going to write this as g of m sorry, this was wrong. It should be m. I'm going to write this as g of m e to the j theta k minus m. And here I'm just using the fact that multiplication in the z domain doesn't matter which order you do multiplication, right? So g star u equals u star g. So I can change the order. Okay? Now the part that doesn't depend on m, I can pull out of the summation. So I'm going to write this as the sum the part that depends on m, e to the j theta k. Okay, so I've just rearranged the sum a little bit. And now we make the observation about this term in the brackets. Two observations. One, this is the discrete time Fourier transform of g of k. secondly, it looks like the summation for a Z transform where we've replaced Z with e to the j theta. 2, it looks like the Z transform of G with Z equal to e to the j theta. Okay? That's legal to do. That is a point in the region of convergence for the Z transform precisely because we assumed that G is Beeble stable. So G is Beeble stable, all its poles are in the unit disk, which means that the region of convergence for its Z transform for G of Z includes, in particular, the boundary of the disk, the unit circle. So this is legal because G is Beeble stable and its ROC includes the unit disk, unit circle, I should say. Okay, so in other words, what we've done is we've taken the Z transform of G and we've replaced Z with e to the j theta. Okay, so what do we conclude from all of this? Steady state output from this input, e to the j theta, k, is the input that we started with, e to the j theta k, times the Z transform, or the transfer function, where we've replaced Z with e to the j theta. Okay? And if you want to write this in polar form, it looks like this. Okay? Fine. But that was for this complex exponential. That's not a signal you're going to encounter, in practice. So we were interested originally in the cosine. And so we can write cosine, of course, using Euler's formula in terms of these exponentials. And so we'll get our final conclusion. Therefore, using linearity and Euler's formula, if the input is now a sinusoid, a regular sinusoid, the steady state output is just like continuous time, except now instead of setting s equal to j omega, like we do in continuous time, we set z equal to e to the j theta. Okay, so notice the similarity to continuous time. Continuous time, you get the same sort of expression, except you would set s equal to j omega, where omega is the input frequency. Here you've set z equal to e to the j theta, where theta is the input frequency. Okay, so example. So here's our transfer function. Beeble stable. And our input is cos of 3k. and we want to find the steady state output. Well, we just evaluate the expression above. So steady state output okay, so just evaluate that expression. So in this case, it's going to be g of e to the j, 2 times, because there's a 2 on the input. So notice theta in this case is equal to 3. And so that 3 shows up in the exponential. Cos of 3k plus the angle. Of e to the j theta k. Right? And then it's a matter of evaluating those numbers, right? So this is very much like what we did in continuous time, except we have to pick the way we evaluate. The points on the complex plane that we would set into G are different. Here we're looking at points on the circle. And so if you do that, I claim you get the following. Okay. And so we have our steady state output. And so what we can do now is we can take all those definitions we had in continuous time for the frequency response, the magnitude response, and the phase response, and we can write them for discrete time systems. So we call the function So the function which takes numbers between negative pi and pi and spits out a complex number, in other words, theta gets mapped to g of e to the j theta, the frequency response. Of g. Okay. And you see there's no point in considering points outside of the interval negative pi to pi because e to the j theta just wraps around the circle. Okay. And so you can also talk about the magnitude response and the phase response. Okay, so I'll say C definition. (682). Okay, so let's make a remark. Why is it? Well, let's make it 2 remarks actually. If we're talking about a kind of a physical system, or a system you're implementing to control a physical system, and you have that the impulse response is real valued. So if g of k which is the impulse response, is real valued, then the magnitude of e to the j theta equals the magnitude of e to the negative j theta. And the angle of this number is equal to negative the angle of the negative number, the complex conjugate. Okay? So what that means is that when you're looking at the frequency response, you don't actually have to consider the full interval from negative pi to pi. You only need to really worry about from 0 to pi. If you look at the response from 0 to pi, that tells you everything about the full response. So when we plot a discrete time frequency response, we only need to consider theta between 0 and pi. Right? We're not losing any information by not looking at the full range from negative pi to pi. Right? In the same way that in continuous time we only plot Bode plots from 0 to infinity. We don't consider negative frequencies because the information about negative frequencies is contained in the information about of positive frequencies. Okay, so let me just draw a little picture here. Of the two kind of situations we have. Okay, so on the left, I'll do the S-plane. On the right, I'll do the Z-plane. Okay, and we have a G of S in the S domain, Bibo stable. And for its frequency response, what do? We set S equal to j omega to get G of j omega. And this is our frequency response. Okay. What we've just discussed in discrete time is the same sort of thing. So you have G of Z, Bibo stable. You set Z equal to e to the j theta. And now you have the frequency response. Okay, and then what do we do in continuous time? Well, first of all, because it's Bibo stable, we know that all the poles are in the open left half plane, which means that the region of convergence for our transfer function is everything to the right of this pole. So here we have in discrete time, we have Bibo stability, and so our poles, maybe they look like this. Say those are the poles of our discrete time system where they're all inside the unit disk. So we'll call this 1. Let's call that 1, negative 1, 1, negative 1. Right, so there's our unit disk, and I'll try to draw a circle. Oh. And so our region of convergence in this case, and this is a confusion, I apologize from previous lectures. I made a mistake in drawing the region of convergence. But our region of convergence is the exterior of the smallest disk containing all the poles. I know I'm out of time, so I'll stop in a second. And so in continuous time, when we do our frequency response, what do? We set S equal to j omega, and then we move up the imaginary axis. In discrete time, what do? We set Z equal to e to the j theta, and theta approaches pi. Okay? And that's kind of the symmetry between the frequency response in continuous time and discrete time. All right, sorry, I went a little bit over. Stop there. I will see you guys tomorrow. I'll stick around for a minute, but otherwise I will see you tomorrow. Yeah, the exams instructions are the same, exactly the same. Maybe I'll post them. If I get a chance later today, I'll post them. Yeah, that's the question that was just asked. Yeah, everything will be the same. Will you be required to MATLAB? Absolutely not. The region of convergence is the region where the Z, in this case, what we're talking about is the Z transform of the impulse response, G. So, in other words, if you think of the transfer function of your system, if you think of it as the Z transform of a signal, it's the Z transform of your impulse response. That is the transfer function. And so the region of convergence is where is it that that Z transform converges, just like it was before. So the other question about MATLAB, you can use MATLAB. It won't really help you in this exam, but you don't have to. So I'll try to post I'll certainly post it before the exam comes out, but I'll try to post the first page like I did last time of the exam. Okay, with that, we can chat again tomorrow about the exam. If there's still questions, hopefully it's clear. See you tomorrow.